Welcome to this lecture number 29 on this NPTEL course on fluid mechanics for undergraduate chemical engineering students. The topic we are currently discussing is dimensional analysis. Okay. We pointed out in the last lecture that dimensional analysis affects a reduction in the number of variables among few dimensional variables. Suppose you have a set of dimensional variables, let us say q1, q2, q3, so on up to qn. There are n dimensional variables. Okay. Then the pi theorem guarantees that there is an functional relationship, let us say capital G, among n minus m non-dimensional groups that are made out of these n dimensional variables, where m is the number of fundamental dimensions in the problem. Dimensions in the problem. Okay. So, these could be mass, length and time in most cases, but if you have heat transfer, you could have mass, length, time and temperature as well. So, example m, L, T, and if you have heat transfer, this is the dimension of temperature. Okay. So, the pi theorem essentially guarantees that you can reformulate a relationship between n dimensional variables into a reduced set of variables. These variables are non-dimensional groups, sometimes called as pi groups. Now, we also outlined the set of steps that one has to follow in order to affect this non-dimensionalization into pi groups. So, steps. Okay. The first step is you first list all the dimensional variables in the problem, relevant dimensional variables in the problem. As I mentioned in the last lecture, admittedly this involves some physical intuition, some engineering judgment as well as some experience that helps in deciding what are the various relevant physical parameters that affect a given quantity. Okay. For example, in the case of drag force on a sphere, we mentioned in the last lecture that one expects the drag force to be dependent on the velocity at which the sphere is moving, the diameter of the sphere, the viscosity of the liquid in which it is moving and the density of the liquid. We have neglected other parameters such as surface tension at the interface between liquid and solid, hoping that that is not a relevant variable for this problem. Now, if indeed the additional variables affect the functional relationship, that will show up when we actually do experimentation. Okay. So, the first step is to list all the dimensional variables in the problem. The second step is to select the fundamental dimensions okay. And this is usually in fluid mechanics problems mass, length and time. Instead of mass, one could use force as a fundamental dimension, but one could use mass, length and time. And if you have heat transfer in your problem, if you have heat transfer and fluid flow, then you have the temperature theta as well. Okay. The third step is now you have to select, okay, and let us say there are m fundamental dimensions in the problem, m fundamental dimensions. If it is m, L and T, it is just 3, m equals 3. In general, you may have m fundamental dimensions. Now, you have to select m repeating variables, okay, Okay. You have to select m repeating parameters or variables, dimensional parameters out of the n dimensional variables, null variables, okay, such that you can construct all the m fundamental dimensions in terms of these variables. In terms of the repeating variables. I will illustrate this soon with an example. Okay. The fourth step is now to represent the fundamental dimensions in terms of repeating variables. And the fifth step is to finally do the non-dimensionalization. Okay. Non-dimensionalize the remaining m minus n variables, m minus n dimensional variables using the result from step 4. Okay. So, this is the essential procedure. Now, I am going to illustrate this for the special case of drag force on a sphere. Okay, we already found out what are the relevant variables. The relevant variables are the force, velocity, diameter, viscosity and density. Okay. So, there are n equals 5 variables. Okay. And the second step is to find out what are the primary dimensions present among these 5 variables. The fundamental, the word I used is fundamental dimensions. If you can list down all the dimensions of these variables, you will find that the fundamental dimensions are mass, length and time, okay, which I will do now. What are the dimensions of various variables? Well, force, the dimensions of force is mass times acceleration. Okay. The dimensions of velocity is length by distance. The dimensions of the diameter of the sphere is simply length. The dimensions of viscosity, as we have seen, is m times inverse length times inverse time. The dimensions of, and finally the dimensions of density is mass per volume, it's ml to the minus 3. Okay. So, if you can see all the variables, you will see that you have m, you have l and you have time. Okay. There is no other fundamental dimension present in this problem. The fourth step is to select repeating variables or repeating parameters, such that you can construct all the 3 fundamental dimensions based on these 3 repeating parameters. Now, there is a element of judgment involved here. For example, I am going to first make a choice and show that it does not work, okay, and then I will do the right choice. All I am trying to say is that you cannot choose any 3 variables. Okay. So, first let me flag off by saying wrong choice. and then I will show why it is wrong. So let us say we are going to choose the 3 repeating variables as f mu rho. Okay. If are chosen, if f mu and rho are chosen as repeating variables, okay, then all we want to do is now represent mass, length and time in terms of these 3 variables. Now, let us see whether we can represent mass in terms of these 3 variables. So, mass times length to the power 0 times time to the power 0 must be represented as the dimension of force, which is m L t to the minus 2 to the power a times, okay, mu to the power b, which is the dimension of mu is m L to the minus 1 t to the minus 1 to the power b times rho power c. If I can find a combination of a, b and c such that this is satisfied, that means that we have found a way to non-dimensionalize mass with a combination of f mu and rho. Now, how are we going to proceed further? We are going to equate. In the first, let me write down, expand these powers out. I can write this as m to the power a plus b plus c, L to the power a minus b minus 3 c, t to the power minus 2 a minus b. Okay. If these 2 equations are equal, dimensionally equal, same, then the exponents must match. Okay. So, we will get the following equations for the exponents. Okay. We will find, we will get 3 equations for the 3 unknowns. If we find a solution, a non-trivial solution to this set of 3 equations, that means we will be able to write mass in terms of the 3 repeating parameters f, mu and rho. Okay. Now, let us try to solve this. The third equation tells you that b equals minus 2 a. Okay. Let us call this 1, 2, 3. Okay. Now, 1 plus 2 implies 2 a, okay, minus 2 c is 0 or a equals c. So, equation 1 then implies a plus b, b is minus 2 a, okay, and a equals c plus c, c is a, is equal to 0. Let me just see this. I am sorry, this is, there is an error here. A plus b plus c is 1, because the exponent of m is 1. So, this is 1. So, a plus b plus c should be 1. So, this should be 1, but this is 0. So, this is inconsistent. The equations are inconsistent, that means no solution exists, okay, which implies that the f mu rho is a wrong choice for repeating variables. Okay. So, it is a wrong choice for repeating variables. Therefore, we have to choose some other set of variables. So, let us now, let me write down correct choice, one of the correct choices, could have others also. So, all I am trying to get at by doing this wrong example is that you cannot choose any 3 parameters and say I will construct all the fundamental dimensions out of them, because as I have just shown, it is not always possible. So, you have to choose those 3 variables from which you can construct all the 3 fundamental dimensions. Okay. So, now let us now try to select the repeating variables as as rho v and d. Okay. Now, let us see whether we can get a mass out of rho v and d. M to the 1, L to the 0, t to the 0 is m L to the minus 3 times A, L t to the minus 1 times B times L to the power C. Okay. So, you have this is equal to m to the power A times L to the power minus 3 A minus or plus B plus C times t to the power minus B. Okay. So, by comparing you will find that A is 1, B is 0, minus 3 A plus B plus C is 0, but since B is 0 you have 3 A equals C, or C is 3 times 1 is equal to 3. Okay. So, what we find is that the mass dimension can be obtained by writing rho to the power A times v to the power B times d to the power C, which is rho to the power 1 v to the power 0 and d cube. So, this means that you can get a dimension of mass by multiplying rho by d cube. That makes physical sense, because rho is mass per unit volume and you are multiplying by d cube, which has dimensions of volume. So, you will obviously get a mass dimension. Likewise, you can get the other two dimensions in the following way. Okay. So, this is mass dimension. So, the length dimension is trivial, because you can choose d as the length dimension, and time dimension we can just choose d by v. Okay. So, d by v is a time scale. So, with these three, now we can non-dimensionalize the remaining 3 variables. So, remember we had a total of 6 variables f, v, d, mu, rho, okay, and we have already chosen v, d and rho as repeating variables. So, they are already chosen as repeating variables. So, we had a total of n is 5 variables and you had 3 fundamental dimensions. So, the pi theorem says that there must be 2 non-dimensional groups, n minus m is 2, there must be 2 non-dimensional groups. Okay. So, the 2 non-dimensional groups must be obtained by non-dimensionalizing f and rho. Okay. So, the dimensions of f are m L t to the minus 2. Okay. So, mass is rho d cube. Okay. In our repeating variables, you can get the dimensions of mass by multiplying rho by d cube. Dimensions of length is d. Dimensions of time is essentially d by v. So, we have time inverse squared. So, we have v squared by d squared. So, force can be non-dimensionalized by the dimensions of force will be the same as rho d to the 4 v squared by d squared, or the dimensions of the force will be the same as the dimensions of rho d squared v squared. Okay. So, you can non-dimensionalize force by rho v squared d squared is a non-dimensional group. Is one of the we have to find 2 non-dimensional groups out of the 5 physical variables. This is one non-dimensional group. What is the other non-dimensional group? We have to non-dimensionalize. So, we have non-dimensionalized the force now. So, we have to still non-dimensionalize viscosity. Okay. So, how are you going to do that? you write the dimensions of viscosity. Okay. Dimension of viscosity is m L to the minus 1 T to the minus 1. So, the dimension of viscosity will be the same as rho d cube, that is mass, length is 1 over d, T is V over d. So, T inverse is d over V. Okay. So, the dimension of viscosity will be the same as, okay. Now, I cancel this d with this d. So, okay, it is rho d cubed, I am sorry, this m L to the minus 1 T to the minus 1, T to the minus 1 is actually V over d. So, let me do this again, T to the minus 1 is V over d. So, you will have 2 d's cancelling d cube to give d squared here to get, okay, finally to get rho d V. So, the dimensions of mu, the viscosity is identical to the dimensions of rho d V. So, if I divide mu by rho d V is a second non-dimensional group. So, we have finally come up with, we had initially a dimensional relationship between 5 dimensional variables. Okay, we have now reduced it to a functional relationship between 2 non-dimensional groups, mu by rho V d. Now, one important thing is that it does not matter whether, so let us call this as pi 1. Okay. We can always write, instead of writing mu by rho V d, we can also write 1 over pi 2 is rho V d by mu. You will get some other functional relationship between these two, let us say g prime of f by rho V squared d squared, and essentially you have 2 non-dimensional groups, and you cannot construct one out of the other. They are 2 independent non-dimensional groups from the original set of 5 parameters. Now, in fluid mechanics, this is called the drag coefficient. This non-dimensional force, drag force, is called the drag coefficient, and this non-dimensional groups rho V d divided by mu is called the Reynolds number. Okay. Now, what is the interpretation of Reynolds number? We will come to that shortly, but essentially what we have tried to show is that by doing this non-dimensionalization, okay, we get 2 non-dimensional groups, and instead of writing the functional relationship among 5 dimensional variables, we can now write it as a functional relationship among only 2 non-dimensional groups. And I have already pointed out the advantage of using dimensionless groups in representing physical data, experimental data, because that immediately allows for scaling up or scaling down, as long as you are matching the non-dimensional groups from the model as well as the prototype. Okay. This we have pointed out extensively in the previous lecture. Okay. Now, I am going to make an additional comment. Okay. Suppose we do experiments. So, essentially we find that f by rho V squared d squared is a function of rho V d by mu. This is what our dimensional analysis is telling you. Suppose you do experiments, experiments tell us, okay, that the following result, that is, let us call this pi 1 and let us call this group pi 2. So, we expect pi 1 is some function of pi 2. Suppose the experiments tell you that the relationship between these two groups is such that pi 1 is some constant by, sorry, this is pi 2. sorry, pi 1 is function of pi 2. So, that is okay. Some constant divided by pi 2. Suppose experimental data tells us this. After doing experiments, you find that pi 1 is some constant by pi 2. Now, what this means is that pi 1 times pi 2 is a constant. So, this is pi 1 times pi 2 is another non-dimensional group, that is actually we can call this pi 3, let us say, is a constant. What is this pi 3? We can write the two non-dimensional groups f by rho v squared d squared times rho v d by mu is a constant. Okay. Now, I am going to cancel the two densities, okay, and what you will find is that f divided by, and we will cancel one length dimension, we will cancel one velocity to give f divided by v d by mu, okay, okay, is some constant. Okay. So, what this means is that rho, which was thought to be a physically relevant variable originally, okay, okay, which was thought to be a physically relevant variable originally, it is dropping out of the function relationship as given by experiments. So, the experiments are telling us that rho is not a relevant variable. This implies experiments imply rho not a relevant variable. I am sorry, this is, yeah, that is okay, rho v d by mu, okay, yeah, that is okay, it is not a relevant variable. Okay. So, this is an important relation that one gets, that just by finding out, so sorry, mu should come here, that was a mistake I was making, mu should just come here. So, f divided by v d mu is a constant, that means rho is dropping out of our entire picture. So, rho is not a relevant variable. So, this tells us a very, very important lesson, that based on our own intuition we may choose a set of variables and proceed with dimensional analysis, and in this simplest case for drag force on a sphere, we found that we have two dimensionless groups, the drag force which is f divided by rho v squared d squared, and then you have the Reynolds number which is rho v d divided by mu. Now, if the experiments are telling us that the drag force is proportional to 1 over Reynolds number, that is what we are essentially saying, that pi 1 is some constant divided by pi 2, then by rearranging pi 1 and pi 2, that is we can re-express that relation as pi 1 times pi 2 is equal to a constant. That means that pi 1 times pi 2 is redefined as a new non-dimensional group pi 3, and that pi 3 has no density in it. So, this in essence this implies that density is not a relevant variable, at least as per the experiments done in a particular regime. Okay. So, if rho is not a relevant variable, you had only, if rho not relevant, you have only 4 variables f, v, d, mu. So, n is 4, you have 3 fundamental dimensions, you have therefore n minus m is only one non-dimensional group as per pi theorem. Okay. Which means that you have this, and that non-dimensional group is just f by v d times mu. Okay. So, when rho is not a relevant variable, then there is only one non-dimensional group. If there is only one non-dimensional group, that there is no functional relation, that non-dimensional group must be a mere number, and that is this constant C 1. Okay. The constant C 1 is a mere number. Okay. So, this new non-dimensional group must be a constant if rho is not a relevant variable. Now, we will come a little bit later, but physically this happens when the viscous effects are dominant compared to the fluid inertial effects, then rho then ceases to be a physically relevant variable. We will point this out a little later when we talk about drag forces on particles and so on. Okay. But right now all I am trying to say is that when we use our physical intuition and judgment to come up with a set of variables, physically relevant variables, but if one of them is indeed not a relevant variable, then that will actually show up in experiments. Okay? That is the point I am trying to drive across at this stage. Of course, we will come to drag forces a little later also. Okay? Now, the next topic I am going to do is to motivate dimensional analysis, not from the point of view of experimentation, but I want to inquire into the physical meaning of the non-dimensional group, such as the Reynolds number. Right now, the Reynolds number emerged purely from non-dimensionalizing a set of a problem, a set of variables such as force, velocity, and so on. If we non-dimensionalize viscosity, we obtain the Reynolds number. Is there a fundamental physical significance for the Reynolds number? The answer is yes, and the answer comes by non-dimensionalizing the Navier-Stokes equation. Okay? So, we want to now non-dimensionalize the Navier-Stokes equations. Okay. The Navier-Stokes equations are simply written as rho times the substantial derivative of velocity is minus the gradient of pressure plus rho g plus mu del squared v. Okay. Now, all these parameters have dimensions. Okay. Now, to be concrete, to give you a physical idea, let us say we are worried about flow past a sphere, the problem for which we just carried out dimensional analysis. So, you could either consider a sphere moving at a constant velocity in a stationary fluid, otherwise stationary fluid, or you could consider the sphere to be stationary and you could have the fluid flowing past a sphere far away, the fluid could have uniform velocity. Both are equivalent formulations, because you could always change the reference frame from a stationary reference frame to a constant to a reference frame that moves with a constant velocity. Okay. So, what we are going to do is, with this problem in mind, we are going to non-dimensionalize the Navier-Stokes equation. So, what are the physical variables? You have the velocity v at which the fluid is flowing far away, you have the diameter of the sphere, okay, you have the viscosity of the liquid, density of the liquid. Okay. Now, these are the parameters that we have, and we want to use these parameters to non-dimensionalize the Navier-Stokes equation. Now, first, lengths. All lengths that occur in the Navier-Stokes equations, there is a natural length scale, they must be non-dimensionalized by the diameter of the sphere. Okay. All velocities can be non-dimensionalized by v and times by d by v. Okay. So, we are going to define x star is the non-dimensional x variable, the x coordinate. Similarly, y star is y divided by d, z star is z divided by d. Okay. Now, we also have gradients in the Navier-Stokes equation. Now, the non-dimensional gradients have dimensions of 1 over length. So, they are obtained by multiplying the dimensional gradient by the length scale d. Now, times that occur in the Navier-Stokes equation, you divide it by the non-dimensional time, okay, and pressure. Okay. Already from Bernoulli equation, we know that P by rho and V squared have the same dimensions. So, we will use this inertial scale for the pressure. Remember that the Bernoulli equation is valid in the strict limit when the fluid has no viscosity, in viscid limit, the frictionless limit, and in the Bernoulli equation, the only forces that are happening are the pressure forces, the inertial forces due to kinetic energy of motion, and the gravity force. So, we can choose the inertial scale rho v squared to non-dimensionalized pressure. Okay. So, when we do all this, we have the continuity equation del dot v is 0. Now, we get d times V times del star dot V star is 0. Okay. This implies that V divided by D, this implies that continuity equation simply becomes del star dot V star is 0. This is the dimensional continuity equation. This is the non-dimensional continuity equation. And as you would have realized by now, all the non-dimensional variables are denoted by an asterisk or a star. Okay. This is the non-dimensional mass conservation equation, differential mass conservation equation. Likewise, we can non-dimensionalize the momentum equation. You have rho dV dt, this is the dimensional equation, is minus del p plus mu del squared v plus rho g. Okay. Now, instead of velocity, I am going to write as dv star, and instead of time, I am going to write t star. Okay. T is nothing but t star times d by v. Okay. So, is minus rho v squared by d del star p star plus mu v by d squared del star squared of v star plus rho g. We will keep rho g as such right now. Okay. Only thing I will write is, I will write g as the acceleration due to gravity vector times a unit vector which is dimensionless. So, it is rho g times g cap. G cap is a dimensionless unit vector. So, we are going to now multiply the entire equation by d squared by mu v. Okay. So, I am going to multiply this entire equation by d, or we can multiply the entire equation alternatively by d by rho v squared, that will be much simpler for us. Okay. If you do that, now the left side will be dv star by dt star is equal to minus del star p star plus you get d by rho v squared times mu v by d squared times del star squared v star plus rho g times mu v by d squared, rho g times or d by rho v squared times rho g times the dimensionless gravity vector, unit vector that points in the direction of gravity. If you consider this combination, okay, this is essentially mu by rho v d, which was 1 over Reynolds number, because Reynolds number, if you remember, we just defined Reynolds number as rho v d divided by mu. Okay. That is one non-dimensional group. Now, the other non-dimensional group, okay, comes from this part. Okay. This is nothing but d by dg divided by v square. Okay. That is the other group that comes about, but traditionally a Froude number is defined as F r is V by square root of G d. So, what you have is 1 over F r squared, 1 over Froude number squared. Okay. So, if you look at this equation, all these terms are non-dimensional. This is non-dimensional, this is non-dimensional, this is non-dimensional, this is non-dimensional, and these two groups that multiply, the viscous term and the gravity term, they are also non-dimensional. One is Reynolds number, other is related to the Froude number. So, we can write the non-dimensional relation, non-dimensional Navier-Stokes equation as dt star, okay, is equal to minus del star p star plus 1 over Froude squared times the, okay, let us first write the viscous term, 1 over Reynolds number times del star squared V star plus 1 over Froude number squared times the acceleration due to gravity vector. Okay. Now, if gravity is not important, that is, if F r is large compared to 1, that means that gravitational force is not important. Not important, because F r is very large compared to 1. So, 1 over F r squared will be very small compared to 1. So, in the limit of large Froude number, what we are, the Froude number, if you see this, can be written as is V, you can multiply and divide by Froude number is essentially a ratio of inertia to gravity. How do you find that? You can simply multiply both the numerator and denominator by, so let us consider Froude squared. Froude squared is V squared by G d. This is nothing but, if you multiply and divide by rho, you have rho V squared by rho G d. Okay. This is a measure of inertial forces, and this is the measure of gravitational head. So, the Froude number is a ratio of inertial forces to gravity forces. So, when the Froude number is large compared to 1, then the inertial forces are much large compared to the gravitational forces in a problem, while if the Froude number is small compared to 1, it is the other way around, the gravitational forces become very important. So, if you consider Froude number large compared to 1, then one can neglect this term. Okay. So, the Navier-Stokes equation will then become simply for Froude large compared to 1 is minus del star p star plus 1 over Reynolds times del star squared V star. So, if we were to solve this, if you solve this, then the non-dimensional velocity field will be a function only of the non-dimensional position, okay, the non-dimensional time and the Reynolds number. There is no other parameter in this equation, because everything is non-dimensionalized. So, there is no geometric parameter like the length of the pipe or anything, or length diameter of the sphere or anything, because you have already non-dimensionalized. So, the non-dimensional velocity can be a function only of these three non-dimensional variables, out of which these are, this is a physical coordinate along the various points in space, this is time, okay, this is non-dimensional time. So, the only physical variable that is under our control is actually the Reynolds number. Okay. This is the only physical parameter that is under control. This is a geometric parameter, it is in the sense as how far you are from the sphere, and this is a non-dimensional time. Suppose you have steady flow past a sphere, steady flow, then the velocity at any point in the fluid will not be a function of time, will be a function of only various spatial coordinates and the Reynolds number. Okay. Now, if you were to find the drag force from this, okay, force is equal to the integral of the shear stress, viscous shear stress, okay, the non-dimensional force will be integral of the viscous shear stress over the surface of the sphere, roughly speaking. Now, this is evaluated at the surface of the sphere. Okay. That means that you are integrating over various positions. So, the non-dimensional drag force will be a function only of Reynolds number. This is exactly what we found even in pure dimensional analysis without worrying about Navier-Stokes equations, but the Navier-Stokes equations also tell the same thing. Okay. Now, another important lesson from this result is that at a given Reynolds number, the velocity is a function only of for a given of the non-dimensional position x star. So, what this means is that suppose I have two systems, you have a tiny sphere and then you have a big sphere, okay, and you have uniform flow past it far away with some velocity v 1, here it is v 2. Now, if you were to ask what is the velocity in the fluid, okay, at a distance x 1, okay, and here at a distance let us say r 1 from the center of the sphere, and at a distance r 2 from the center of the sphere. Okay. Now, if the Reynolds number is same for these two problems, if R e for system 1, this is system 1, this is system 2, is the same as R e for system 2, then the non-dimensional velocity for system 1 will be identically equal to the non-dimensional velocity for system 2, okay, at same non-dimensional distance r star, okay, at same r 1 star is r 2 star. R 1 star is nothing but r 1 star is nothing but r 1 divided by d 1, the diameter of the tiny sphere. R 2 star is nothing but r 2 divided by the diameter of the bigger sphere. If you ensure that r 1 star is r 2 star, then the non-dimensional velocity at a given non-dimensional position is the same if the Reynolds number is the same. So, if you were to do experiments or numerical simulations, not just to find integrated quantities like drag forces, but even point-wise variations, this non-dimensionalization of the Navier-Stokes equation is telling us that it is not necessary to solve these two problems individually separately. Okay. If you want the information at the same Reynolds number, okay, then the velocities of these non-dimensional velocities of these two different systems will be identically equal if you are looking at the same non-dimensional position, okay, which is r divided by d. So, this is a very, very powerful result, because this means that you do not have to do computations or experiments for these two problems separately. Once you non-dimensionalize them, once you solve one problem, you have solved a whole infinitely large number of geometrically similar problems, okay, and that is a very, very, very important simplification. Now, let us also come to the interpretation of Reynolds number, which I promised few minutes back. Okay. Reynolds number is written as rho v d divided by mu, which can be written as rho v squared divided by mu v divided by d. This is the ratio of inertial forces in the fluid. Remember that rho v squared is a measure of fluid inertia, it also comes in the Bernoulli equation, to the viscous forces in the fluid. Remember that the Newton's law of viscosity tells you that tau x y is mu times partial v x by partial y in the simplest case. If you estimate this as v divided by d, then mu v divided by d is a typical estimate of viscous stress present in the fluid. So, inertial forces or inertial stress to viscous stress. Okay. So, roughly speaking, Reynolds number is ratio of inertia to viscous forces in the fluid, and it is a pure number. If the Reynolds number is very large compared to 1, then one can anticipate that inertial forces will dominate the flow. and if Reynolds number is very small compared to 1, then one can guess that the inertial forces will be small compared to the viscous forces. Okay. So, this is another important thing that comes across in non-dimensionalization. Now, finally, we will discuss similitude and scale up. I pointed this out earlier itself, but let me also discuss this again, okay, in the context of an example. Okay. Suppose I have the motion of a sphere with diameter d, okay, and d1. Okay, so, let us call the diameter of the sphere as small d1, and the diameter, it is, let us say it is moving in a pipe of diameter capital D1, and you have another system, a tiny sphere of diameter small d2 moving in a pipe of diameter capital D2. Okay. Let us say that the sphere is, the center of the sphere and the center of the axis of the pipe are identical in both cases. Okay. Now, when are these two systems dimensionally similar? When are these two systems similar? First requirement is geometric similarity. That is, you must have, by geometric similarity we mean that you should have a cylinder, I mean a pipe here and a sphere here, you should have a pipe here and a sphere here. Not just that, but the ratio of d1 to d1 should be the same as the ratio of d2 to d2. Okay. So, unless this happens, these two systems are not geometrically similar. Moreover, we have assumed that the center of the sphere and the center of the axis of the pipe are coinciding in both the cases. If it is, if let us say in one of the cases it is eccentrically placed, again geometric similarity is violated. So, we can say that these two systems are geometrically similar only when all the length scales in the problem have the same ratios. Okay. So, we should have first of all the distance of the center of the pipe, okay, and the distance the center of the pipe and the center of the sphere to coincide on the same axis, and we should also have the ratios of these two length scales, okay, to be the same, otherwise geometric similarity is not possible. Okay. Now, that is one important similarity. The second requirement, okay, is kinematic similarity. So, if this is not the case, then you will not have geometric similarity. Okay. Another illustration of geometric similarity, suppose you have an ellipsoid. Okay. Suppose the major and minor axis are by the ratio of 4:1, you have another ellipsoid, you have 3:1, okay, then these two are not geometrically similar. So, all the length scale ratios must be the same between two systems when some things are geometrically similar. Okay. And there are two more similarities, namely kinematic similarity and dynamical similarity. I will come to that in the next lecture, and these are very powerful ideas that help us in scaling up and scaling down various experimental data from laboratory to a real industrial device. We will stop here at this point and we will continue in the next lecture.